to a circle. Be mindful that this is a video, so if I go too fast or you need to review something, you can always pause and rewind. So we're going to talk about tangents to a circle. So let me draw a circle, and let's go over what a tangent is. What does that mean? So a tangent line or segment to a circle is a line or segment that touches a circle exactly at one point. Okay, so in this circle, let's call this circle A. We could say that segment BC or line BC is tangent to circle A at point B. Point B, that line there, where the line and the circle meet, is called the point of tangency. Now there's a special relationship that tangents or tangent segments have with a circle. One relationship we're going to talk about is its relationship to the radius that is drawn from the center to that point of tangency. Okay, let's first go over something that we should know though about radii. Okay, so in a circle, there's a theorem that tells us that radii in the same circle are congruent. So sometimes I write it as a shorthand, so radii in the circle are congruent. Okay, so that's actually a basic concept that some of you should remember from previous encounters with circles. So if, say, this is circle A, a radius is a segment that extends from the center of a circle to the edge of the circle. So this is AB. So let's say AB is 10. That means that any segment I draw, A to C, AC would also have to be 10. Okay, radii, all of these radii that I'm drawing are all going to be 10 units. Okay, they're all the same. Okay, so radii of the same circle are congruent. So radii of the same circle are congruent. Okay, so that's one basic thing we need to review. So let's go back to the relationship I said that a radius has with the tangent line. So if I were to draw again a circle and then construct a line that is tangent to that circle at one point, so let me redraw this here. I'm going to move this down to make it appear to touch at exactly one point. We'll call this point B. Okay, and call this circle A. So in circle A, you'll notice that when I construct the radius so that it meets that point of tangency, you might notice that the angle that is formed between the radius and this tangent line appears to be 90 degrees. If I were to measure it, it would actually be exactly 90 degrees. So one part of this theorem, if a line is tangent to a circle, then the line is perpendicular to the radius that meets at the point of tangency. Okay, so I'll allow you though, if you were writing a proof or just explaining, you could just tell me that the radius is perpendicular to the tangent line. It's implied that it's perpendicular at the point of tangency. Now, if the opposite was true, say you didn't know that it was if the line was tangent. Okay, so look here, let's call this BC. Say you didn't know it was tangent, but all you were given was that ABC was a right angle. Well, you could state that if you know that, so if a line is perpendicular to the radius at the point of tangency, then we know that line has to be tangent to the circle. Okay, so if a line is tangent to a circle, it's perpendicular. If the line is perpendicular, that means it's tangent to the circle. So let's do a practice problem. The question is AB tangent to circle C? So AB is this segment. I'm going to highlight it here. So we're trying to figure out, is it tangent to the circle? Well, if this is circle C, that means that CA has to be a radius. How do I know? Well, a radius is a segment that extends from the center to the edge of the circle. Okay, so we're going to check. Well, let's pretend that AB was tangent to the circle. If that were true, that means that angle CAB would have to be a right angle. So the question is CAB a right angle? So let's check. If CAB were a right angle, if you look, we have 6, 8, 10. We have a triangle with 3 sides, 6, 8, 10. If this were indeed if CAB were a right angle, that would make the triangle a right triangle. So let's check. Does A squared plus B squared equal C squared? So does 6 squared plus 8 squared equal 10 squared? So I get 36 plus 64 equals 100. Yes. Because CAB is a right triangle, this being the hypotenuse, that means that AB is tangent to circle C. Why? Let's go back. Because if a line is perpendicular to the radius, then it is tangent to the circle. So yes. Here's another theorem I'd like for you to go over. So there's another theorem in this section called the two-tangent theorem. So what the two-tangent theorem looks like is if I had a point outside of a circle, let's call this point A, and I were to construct two tangent segments from that. So I'm going to construct one here. Try to make that look like it touches only at one point. Let's construct another one here. So I'm going to label the points where they meet the circle. So I say this one meets there, and that one meets there. So I'll call this B, and I'll call this C. If I were to take my ruler and measure this segment from A to B, and if I were to take my ruler again and measure from A to C, that segment, I would notice that those two tangent segments would be congruent. So AB equals AC, or you can say AB is congruent to AC. The two-tangent theorem tells us that if there's a point outside of the circle, the two tangents that extend from it would be congruent, the segments. Okay, so just from segments are between 2 points, correct? So between B and A, and between C and A, those segments would be congruent. Let's do a practice problem where we have to apply this knowledge. So here's a practice problem. It says, find AB and AS if the radius in the circle is 5 and if AD is 13. So if you look at the picture, I'm going to have to construct a few things. Let's first, so actually there should have been more information in the given. I should have been also told that AB and AS are tangent segments. Okay, that's an important part, because then I'm allowed to, so I'm just going to put that in your instructions now. Okay, so they're tangent segments. The radius in circle D is 5. So if I look at the picture, there's no radius drawn, but I know if I connect B to D, that's going to be 5 units. And if I connect D to S, that's also going to be 5 units. Why? Because radii in the same circle are congruent. D to B, D to S, those are both radii. Okay, it says AD is 13, so let's actually construct AD. So from A to D, it says it's 13. And then let's figure out what else do I know that could be helpful. Well, if AB and AS are tangent segments, we know that the radius is going to be perpendicular to the tangent segment. So that means that this angle is 90 degrees. And the same is true for the other triangle. The radius is going to be perpendicular to that tangent. So if I'm trying to find the length of AB and AS, first of all, if they're tangent segments based on the two tangent theorem, I know that they're going to be congruent to each other. So now all I have to do is figure out what they would be. So let me just draw one of those triangles out where the radius was 5, AD was 13, and that unknown side, we'll just call that A. Some of you might look at this and know that this is a Pythagorean triple. If you don't recognize that it's a Pythagorean triple, it's a 5, 12, 13. So this is going to be 12 units. If you didn't notice that, that's okay. We could use Pythagorean theorem. When I use the theorem, a squared plus 25 equals 169. A squared equals 144. And then when I take the square root, a would be 12. So the question is, find AB and AS. They are both 12 units. From here, I have some practice problems I'd like for you to do. Here's the first. set. You can pause the screen and try the problems. Here's the third problem. You can pause and try this problem. And here's the fourth. You can pause and try this problem. We will review the 4 problems in class.